Hi everyone, in this video we are going to examine the behavior from a classical mechanical point of view of an infinite one-dimensional chain of masses connected up by springs. Now you can either think of this as just an interesting classical mechanics problem, or if you want to think of this as having an application, then what we're doing is really building up a simple model of atoms in a crystal where the masses in our chain are the atoms and the springs are the chemical bonds between them. And the vibrations of the masses that we're going to solve for are what we call phonons, which are collective excitations in a crystal, which is something that gets studied in condensed matter physics. So let me just first set up the problem and talk you through what's going on in this diagram that I've drawn out. The top row here, this bit here, is our chain of masses at equilibrium, at rest. And there's a couple of key parameters marked on. So each spring has a spring constant of k, all the same, and each mass has a mass of m, all the same. And the system's equilibrium configuration has all of the masses equidistant from each other. That distance is going to be called d, which is not necessarily the same as the natural length of the springs. I'm not writing on to my diagram the natural length of the springs because it turns out that's not going to affect our solution, as we'll see a bit later on. So then in the second row of my diagram down here, we've got a more general configuration of our chain where each mass has been displaced a little bit from its equilibrium position. So these dashed lines here are showing where the original equilibrium positions were, and each mass has been displaced by an amount which I'm calling psi, not to be confused with quantum mechanical wave function. I'm calling this psi instead of x because I'm going to introduce something else called x later on. So each mass has a displacement of psi from equilibrium, and we index the masses by a subscript, which I'm calling n in general. So here's the nth mass has a displacement psi n. Of course, the one on the left has psi n minus 1, the one on the right has displacement psi n plus 1. And the question is to figure out the displacement psi n is a function of time, so how each individual mass varies with time in terms of its displacement. And of course, once we've solved for psi n of t, we also want to spend a bit of time interpreting that solution and thinking about what it means physically. But anyway, the easiest way to get set up, if we're doing classical mechanics, is just to apply Newton's second law to an arbitrary mass, the nth mass. So I'm going to say n2l, Newton's second law, applied to mass n. Your mass times acceleration is just going to be m psi n double dot. And if you look at, this is the mass here that we're focusing on, right? There's going to be a spring pulling to the right and a spring pulling to the left. Well, in general, they could be either pushing or pulling, depending on whether the springs are in compression or whether they've been extended. But we're going to set this up in a general way and just write down the forces. So the force due to the spring on the right is going to be k times the extension. So we just put our spring constant k. The extension, well, let's start by writing down an expression for the length of that spring, the one on the right. And the length in equilibrium was d. The mass on the far right has moved to the right by displacement of psi n plus 1. So the length gets longer by that amount. We add that on. And our nth mass itself has also moved to the right, but because that mass is on the left end of the spring, when it moves to the right, it tends to compress the spring. And so this psi n gets a minus sign, minus psi n. This bit here is the total length of that spring. Then we subtract off the natural length of the spring to get the extension. I'm just going to call that L. We'll see that it's actually going to cancel in a moment. So then all I have to do is include the force from the spring on the left as well. This one gets a minus sign because the spring's on the left. And we just need to do basically the same thing. So write down the extension of the spring, start with a length of d. When mass n moves to the right, it tends to extend the spring on the left. So psi n gets a plus sign this time, and for the same reason, you get a minus psi n minus 1. You subtract off the original length, sorry, the natural length, I should say. So let's see what we can do with this. I'm going to divide both sides by m just to make the left-hand side nice and simple, psi n double dot. If you think about what happens when you expand the brackets, you're going to get a kd that cancels out with a minus kd, and similarly a minus kl that cancels out with a plus kl. which is why, as I said earlier, your solution doesn't end up depending on the natural length of the springs. Now, I'm mentioning this explicitly because it wasn't super obvious to me. I kind of had some intuition that, like with transverse waves on a string, maybe if you had more tension in the springs to start with, the waves that end up propagating along the chain might be faster. It turns out that's not actually the case, which makes sense when you think about it, because it's really only the imbalances in the forces that are causing the motion rather than the actual original tensions themselves. But anyway, the simplest way to write the right hand side is, well, you've got your k over m because we divided by m. You've got a psi n plus 1. You've got a plus psi n minus 1. And then you've got a psi n from each term. Both of them have minus signs. So you've got minus 2 psi n. I'm going to define a new parameter, omega naught squared, which is defined as k over m, and then I'm going to replace that k over m with omega naught squared. This, of course, is just the frequency of free oscillations of a single mass spring system. So how are we going to go about actually solving this? Well, there's going to be a mix of intelligent guesswork and a bit of algebra. The first thing I'm going to do is point out that the equation we've got here, the equation of motion, looks kind of like a simple harmonic motion equation if you ignore those psi n plus 1 and psi n minus 1 terms, right? If you didn't have those terms, this would just be a simple harmonic oscillation of psi n. So that kind of leads us towards guessing an oscillatory solution in time for psi n. So let's try that. Psi n is going to be some amplitude times an oscillatory part, e to the I omega t. This an could be a complex number. Let's make a note of that. So an is a complex number which includes both an amplitude and a phase, which could in principle both depend on n. So if we take that trial solution, what's going to happen? We substitute it into the equation. The second time derivative of this, well, you pull down an I omega each time you differentiate with respect to time. So overall, you pull down a factor of minus omega squared. The left-hand side is going to be then minus omega squared, an e to the I omega t, but I'm not even going to bother writing e to the I omega t because that's going to be present in all of the terms. That's going to cancel from both sides, right? The right-hand side still got your omega naught squared. Then the rest of this is easy to write down. We don't even have to differentiate, right? You're going to get an a n plus 1 from the psi n plus 1, and similarly for the other two terms, right? So plus a n minus 1 and minus 2an, where we've cancelled down all of the oscillatory terms from each individual term. Then I am just going to put all of the terms on the same side, make the equation equal to 0, and I'm going to first actually divide by omega naught squared, just to get rid of the brackets. So if you do that and then move this term over to the right, you're going to get omega squared over omega naught squared, an, but also this minus 2an here. So minus 2 goes in the brackets. Then, of course, you've still got your a n plus 1 and a n minus 1. All of that is supposed to be equal to 0. So this is looking promising. But now what we've got to do is solve this recurrence relation, right? We've got these complex numbers, an, the complex amplitudes, and this is the recurrence relation for an. So I've seen various different attempts to justify the solution of this recurrence relation in all the various different sources that I've seen. They all involve a bit of guesswork to varying extents. My solution is going to involve also a bit of guesswork, but I'm going to try to be as careful as possible in talking you through the logic here. And what I want to do is use what's called the characteristic polynomial method of solving recurrence relations, which is basically where you try a solution of the form an is proportional to some number r to the n. Here, remember the an's were complex, so this capital A and this r could also be complex as well. I'll make a note of that. So a and r could both be complex. The justification of this is simply because it works in the same way that when you're trying to solve a second order differential equation, one of the first things you try is substitute an exponential in to the equation because it works, right? And then you kind of tune the parameters of your guess to make it fit the particular equation you're looking at. That's basically what we're doing here. This is a standard technique for recurrence relations. So if we just substitute that into the previous line, then we are going to get, we've still got our omega squared over omega naught squared minus 2. An, of course, just becomes a, capital A, r to the n. Then all we have to do for the other two terms is change the power of r, right? So the next one is capital A, r to the n plus 1, and then plus capital A, r to the n minus 1. All of that is equal to 0. Notice that the a's cancel, which basically means there's no restriction on a, right? A can be anything. So here's the reason the characteristic polynomial method works. It's because the r to the n can be cancelled from each term. So if we cancel down r to the n, you get omega squared over omega naught squared minus 2. That's now just a constant term. Then you've got plus r, because this was r to the n plus 1. We got rid of the n by dividing by r to the n. Similarly, for this term, you're just left with r to the minus 1. And we're left with a reasonably simple looking equation to solve for r. So we're trying to solve this equation for r. One thing you could do, the standard sort of thing to do with this equation, is multiply up by r, and then you get a quadratic which can be solved. However, I'm going to try to simplify things a bit, well, quite a lot really, by referring to the physics of what's going on here rather than taking a purely mathematical view. And think about what the meaning of r actually is, right? So firstly, remember that r was a complex number. So what we can do is write r as its modulus times e to the I phi, where phi is the argument of the complex number r. Okay. Now, if we use that representation, go back to the fact that psi n was an e to the I omega t, and an was big A r to the n. Pull all that together, and you conclude that psi n is, so you've got your a, you've got mod r to the n, right, because r itself was raised to the power of n. Then you've got e to the I phi to the power of n, which is the same as e to the I n phi. And then you've got your e to the I omega t. So physically, what does this mean? Well, the e to the I omega t is just telling us that each mass is oscillating with an angular frequency of omega. The e to the I n phi is telling us that the phase of each mass's oscillation is n phi. Right? Remember, n is just the index of the mass along the chain. So an equivalent way of viewing that is that each mass differs in phase from the mass before it by an amount phi. We don't know anything about phi yet, right? But so that part of the solution is just a phase offset in the oscillation, and this whole prefactor a r to the n, a mod r to the n, is the amplitude of the oscillations. Now think about what would happen if mod r were bigger than 1. If mod r is bigger than 1, then as n gets larger and larger, the amplitude of the oscillations gets larger and larger. Now, we don't have some sort of energy input into our system, right? So it doesn't really make physical sense that as you go along the chain, the oscillations just get bigger and bigger. Where's that energy coming from? Similarly, if mod r were less than 1, the opposite would be true, right? The further to the right you go along the chain, the bigger n gets, the smaller the amplitude gets. And that doesn't make physical sense because there's no energy loss in this system. We haven't assumed anything about there being a damping mechanism in the springs. So we kind of come to the conclusion that we are going to require the modulus of r to be exactly 1, and I've argued that on the basis of energy considerations. Now, as it turns out, requiring that the modulus of r is 1 greatly simplifies this equation up at the top that we're trying to solve. Let's see how exactly that works. So we get, well, we've still got our omega squared over omega naught squared minus 2. R is now just e to the I phi because its modulus is 1. And then the r to the minus 1 becomes e to the minus I phi. All of that, of course, is still supposed to equal 0. Let's keep the constant term as it is. Now we can use the relationship between complex exponentials and trig functions, right? E to the I phi is cos phi plus I sine phi. E to the minus I phi is cos phi minus I sine phi. So the sines cancel, and you just get 2 cos phi, which is very nice. Then we can rearrange this a little bit. I'm going to get the omegas on one side and the phi on the other side. So omega squared over omega naught squared is, let's factor out a 2. You've got 2, it will be 1 minus cos phi. We can actually make the right hand side look a little bit nicer using sort of trig identities. Make a couple of notes down the bottom here. Note that in general, for some arbitrary theta, cos of 2 theta is 1 minus 2 sine squared of theta. I'm not going to prove that. It's a standard double angle identity. But one of the implications of this is if you move the terms around and replace theta with theta over 2, in other words, just relabel your theta to theta over 2, then you get 1 minus cos of theta, right, because it's 2 theta over 2, is 2 sine squared theta over 2. Right, these are basically just different versions of the same thing. So 1 minus cos phi is 2 sine squared of phi over 2. Having quickly proved that, I'm just going to delete those and then use the result. We've now got 4 sine squared of phi over 2. And we can even square root both sides and come to the conclusion that the angular frequency omega is related to phi via omega equals omega naught times, sorry, there's a 2 as well, isn't there, because there's a 4 there. So 2 omega naught, and then modulus of sine phi over 2. You need modulus signs because by definition the square root is positive. So square root of sine squared is not just sine, but it's modulus of sine. So I've just left some of the key results up at the top right there. We're now at a stage where we can start to put all of this together and understand what the solution really means. So given all of these intermediate results that we've got, here's our psi n. Let's write that in like a final form. So psi n is, you've got your a, this is the amplitude, could be anything. We said that mod r has to be 1, so mod r at the end disappears. Let's combine these complex exponentials into a single complex exponential. So e to the I n phi plus omega t. Now if we introduce an x coordinate such that x just runs from left to right, doesn't really matter where the origin is, then we can write that displacement in terms of x instead of in terms of n, right? So the way this would work, if we drop this subscript n, we can say psi is ae to the I. Well, to get n, the number, the index of the mass, you would just take the x coordinate of the mass and the undisturbed x coordinate of the mass, I should say, and divide it by the length of the spring. That should, because you're basically then counting up how many spring lengths fit into the distance between the origin of the x-axis and the x coordinate of that particular mass. And so if we use that idea, your n can be just written as x over d. The rest of this is the same, so x over d phi plus omega t. And you can go one step further and redefine phi over d as a new parameter. So we've got ae to the I. Let's call phi over d k. So we've got kx plus omega t. Make a note that we defined k to be phi over d. Now, what's the point of all this? Well, hopefully this might look familiar, right? Some amplitude times e to the I kx plus omega t is our standard solution for a wave. And for this kind of wave-like solution, k is the wave vector, omega is the angular frequency. It kind of looks, as I've drawn it here, as if we've got a wave that's traveling to the left. The sign doesn't really matter. It's just if we had a negative k, it would be traveling to the right. And so the direction of that wave depends on the sign of k. Omega is a frequency, so by definition, it's positive. And this here, k is phi over d, is also consistent with the idea of k being a wave vector, right? Wave vector is basically just a quantity that tells us how much phase cycles through per unit distance. Now, one thing that we're often interested in when we're studying waves is what's called the dispersion relation, which tells you how the frequency, the angular frequency, is related to the wave vector. Now, For certain waves, like small amplitude waves on a string, transverse waves on a string, the dispersion relation is just linear. All waves just go at the same speed. But here, because of this equation here, the speed of the waves is going to depend on the frequency, or equivalently depend on the wave vector. Just to make this even clearer, I'm going to replace this phi here, using the fact that k is phi over d. I'm going to replace this phi with kd, and then we've got a nice explicit relationship between omega and k. So let's focus on positive k first. We've just got like a sine curve. I'm going to plot the sine curve up to its first maximum, and I'll explain why I'm doing that in a second. So sine curve just going to look something like this. Watch this wave vector here, going to be, well, the maximum of the sine occurs when its argument is pi over 2. Therefore kd is pi, or k is pi over d. This maximum value here is going to be 2 omega naught. Remember, we said that k could also be negative, representing waves going in the opposite direction. Because of the modulus sign, you've got exactly the same shape. It doesn't go negative like a sine curve usually would. You've taken the modulus, so it's going to look something like this, ideally symmetric with the branch on the right, and you've got your minus pi over d there. Now, why have I only plotted the graph between minus pi over d and pi over d? Well, you could extend it as far as you wanted in either direction of k, but notice that this point here, when k is pi over d, because k is in general phi over d, that corresponds to the point where phi is equal to pi. And similarly, the point on the left, the far left, corresponds to the point where phi is minus pi. Remember, the interpretation of phi was it's the phase difference between the oscillations of successive masses in the chain. Now, of course, phase difference is only uniquely defined in a range of sort of width 2 pi, right? In other words, a phase of 2 pi plus something is totally equivalent to a phase of just that thing, right? And the phase doesn't have to be defined from 0 to 2 pi. It can be any range with a size of 2 pi. For example, minus pi to pi, it's nice and symmetrical. And so the idea here is, on our graph, the phase difference between successive masses goes from minus pi to pi. If we were to extend our graph, it would be valid, but it wouldn't be representing something that's physically different because of the fact that the phase is cyclic in that sense. So we conventionally only plot this dispersion relationship over this range of k values. So you've got this interesting situation where infinitely many different wave vectors actually represent the same thing happening physically, which is very different from what you'd expect from waves in a continuous medium. It's basically to do with the phenomenon of aliasing, where because you only have masses at certain points, right? You don't have masses everywhere, but only at certain points along the chain, you're only sampling that wave at certain points. One final interesting feature of this graph I want to point out is the gradient d omega by dk is the group velocity of the waves that are traveling along our chain. And you can see the gradient, because it's a sine curve, the gradient gets smaller and smaller as you go up here, right? So as k increases to its maximum unique value, the group velocity of the waves is getting smaller and smaller. In fact, the gradient of the curve is 0 here because it's a maximum of sine. And so that's telling you that if you have a wave vector of pi over d, you actually have a standing wave. This is essentially because phi is pi there, right? And so each mass is in antiphase with the mass that came before it and the mass that came after it. Might be a little bit difficult to visualize, but I suggest you go to Wikipedia's page on phonons, and they have a nice animation of the different vibrational modes for various different values of k, and you can see the standing wave character of that maximum k mode. So that's all for this brief introduction to phonons. Thanks for watching, and see you soon.